Welcome to the lecture series of KT Semicon. So in today's lecture, we'll start the CMOS module. Okay. So in this module, we'll explain the complete things related to CMOS, why we are using CMOS in VLSI, what is the need of CMOS, right? We'll explain all these things. Okay. So let me share my screen. Okay. I hope my screen is visible. Okay. So CMOS means complementary metal oxide semiconductor, right? So this is the one of the transistor, right? So why we are using this CMOS in particularly in VLSI, I'll explain. So how a CMOS is going to be used in VLSI, and CMOS is the foundation of modern electronics. So CMOS is one of the transistor, right? So if you want to make one logic, so by using these transistors only we can build that logic, right? For mugs also, for flip flops also, any electronic device, we are going to make the device logic. So in that, these transistors are used. Okay, so here CMOS is also one of the transistors. So by using all these transistors, by combining all these transistors, we are going to make one logic. That logic is either maybe mux or else flip flops or else any electronic component that is going to make by using these transistors, right? So here CMOS is the complementary metal oxide semiconductor transistor. So what is the operations and all, I'll explain. Okay, so before going to that, we need to know what is meant by VLSI. Okay, so VLSI means very large scale integration, right? Very large scale integration. So integration means, so let us assume, okay, this is my silicon chip. Okay, this is the width of my silicon chip, and this is the particular height. Okay, so this is the height of this particular silicon chip. This is my silicon chip. So we are going to be integrated, which means we are placing the transistors. What is the count of the transistors? Millions or billions of transistors we are integrating means we are placing all these transistors within this particular area. Okay, so this is the process. VLSI stands for very large scale integration. It is the process of creating an integrated circuit. So this is my integrated circuit, right? So by combining millions or billions of transistors onto a single silicon chip. So this is my silicon chip. So in this particular area of this silicon chip, we are going to integrate, which means we are placing all these millions of billions of transistors in a single silicon chip. So after that, it is turned into a particular IC, right? So this is the one of the IC. So this is how my VLSI works and all. Okay, so before VLSI, we are having computers were huge. Why? Because so before VLSI, we are having some LSI, which means small scale integration, and medium MSI. Okay, sorry, medium scale integrations. So sorry guys, 1 minute. Okay, so by using this particular transistors, so my computer size was big in before VLSI. Why? Because we are using LSI and medium scale integration. So in that integrations, we are having the size of transistors is more. If my transistor size is more, then what happened? So obviously my logic is going to be more, because I just want to construct, I just want to make one computers, right? So in computers we are having so many logics means by combining the transistors we can get one logic, right? So I'm having some logic. That logic is having 1,000 count of transistors, which means we are building that logic by using this 1,000 transistors. So if I want to place these transistors, which means if I want to make one logic, then we need to place these 1,000 transistors on a particular IC. So in LSI or MSI, my transistor size is more. If my transistor size is more means I need to use more space, right? Because my transistor size is more. So if I want to place all these 1,000 transistors in a particular silicon chip, my silicon chip size is more, right? If my silicon chip size is more means obviously my electronic device size also more. That's why before in LSI and medium scale integrations, electronic component size is more. Okay. And after VLSI we are having only very tiny, which means very small, right? We are working on nanometers, right? 28 nanometers, or currently they are working on 7 nanometer, 2 nanometer, like this, right? So what happened now? So my transistor size is less. Okay. So if my transistor size is decreases, obviously my electronic component size also decreases. Sorry, my present in VLSI, we are having a less size of transistors. If my transistor size is less, obviously my electronic component size also less. So this is the thing actually happened. So affordable chips like a smartphone, right? So smartphone is the best example for present electronic components, right? So this is the thing, and these are the integration evaluations. So in 1960s, okay, we are having small scale integrations. What is mean by small scale integrations? We are going to place only 1 to 10 number of count of transistors. See, I'm having one particular size, okay, with some width and height of that particular chip. Okay. So for this shape we can place only 1 to 10 transistors count only. In which integration? In small scale integration. So after moving to MS mid scale integration, so within the same place we can do up to 500 count, right? So why? Because my transistor sizes decreases. If my transistor sizes decreases, it will occupy more count of transistors, right? So this is the process here. 7400 is one of the example for small scale integration. So this is the NAND gate logic, right? NAND gate IC number, correct? So after that we are having another one also, medium scale integration. So for this medium scale integration, this is the example. I think this is the encoder example. Okay. So after that we are moving to large scale integration. Again in large scale integration we can happily place up to 20,000 count of transistors. Okay. If it crosses more than 20, see, if I'm having 22,000 of transistors. Okay. So here my logic is built by using some 22,000 count of transistors. Now what happened if I want in, I'm at large scale integration, if I want to place this 22,000 cells, 22,000 transistors, what should I do? I need to take two silicon chips, right? Okay. For this particular chip in small scale integration we can place up to 20,000. Okay. So after 20,000 we cannot place the remaining transistors. That's why we need to take another silicon chip also, right? So at this stage more it will take more cost also, right? Because a silicon chip is more cost also, right? So after that we are having VLSI. So in VLSI we are having 1 billion plus transistors, right? So this is, we are placing millions or billions of transistors in a single silicon chip. So we are now stuck at VLSI. So after that also we are having gigascale integration also. Right. So up to now VLSI is not, VLSI is much more enough to us to place all this logic. That's why we are not completely moving to GSI. We are stuck at VLSI. Okay, this is enough for particular point. Okay, so this is the thing happening. So why VLSI is matters? Okay, so here miniaturization. Miniaturization means small size. Okay, as compared to LSI and MSI, particularly my VLSI chip size is less because my transistor size is less, right? So that's why VLSI is mainly for miniaturization, which means very small size. Okay, nanometer size, right? So after that, cost also efficiency. So if you are moving to gigascale integration, so VLSI is enough. Okay, even though VLSI is enough, we are moving to gigascale integration. Then what happened? So obviously my cost also increases, right? So VLSI is more somewhat cost efficiency as compared to GSI. Okay, and as performance wise also it will give better performance results also, and my power efficiency also within budget. Okay, so within budget we need to run the complete logic by using certain power. Okay, reliability. Okay, reliability means how long it will perform. All right, what is the major difference between performance and reliability is performance means how accurately it will working. Okay, reliability means how long it will working, right? So this is the main things why VLSI matters. Okay, so ASIC versus FPGA, right? So I think you guys are very familiar with these things. ASIC means application specific integrated circuits, right? So in this particular circuits already my design is complete. See, we are having one logic. Okay, so I'm having some AND gate. Okay, so this AND gate having A and B as inputs and Y is my output. So what has happened now? So in particularly in applications specific integrated circuit, my logic is completely okay. See, this is my logic, right? This logic is completely manufactured in this. This is my silicon chip. Okay, this is my silicon chip. So my silicon in on my silicon chip, I'll make some logic, manufactured some logic in it. Okay, so according to ASIC, my logic is completely manufactured. Okay, which means we cannot change the logic. Why? Already my complete logic is manufactured. If I want to change my logic, we cannot change the logic because it is manufactured, right? So as compared to FPGA. So FPGA means field programmable gate array, right? So which means within that particular silicon chip, we cannot manufacture any logic in it. We just integrated one IC. If we want to change the logic also, see, before thing will manufactured, which means I'm having some logic. Okay, A and B are the inputs and Y is the output. So this is my one of the particular indicate logic. So in this particular ASIC, my logic is completely manufactured, which means it is physically manufactured on this silicon chip. Okay, we cannot change. If I want to change the logic, we can change. We cannot change. But in particularly in FPGA, if you want to change this logic, so this output will I'll came this output very nicely. So I just want to change my logic. So if I just want to change my logic also, we can remove that logic and we can again reconfigure it, which means we can change whatever we want. Okay, so this is the major difference between ASIC and FPGA. See, the main example for both of them are, so army people are carries one knife, right? Army knife. Okay, that army knife is better example for this FPGA. Why? Because that army knife is particularly they use it for like a knife, and if they want scissors, they use that army knife as scissors, and if they want to cut any trees or something, they use that army knife as saw also, which means they are using that particular army knife for three different tasks. However they want, they'll use according to the according to the task. Okay, if they want to change the task, they'll change from scissors to knife, knife to saw, like that they'll change. But in ASIC, in ASIC is like a kitchen knife. Okay, so we can use kitchen knife only for cutting purpose. We cannot use it as a scissors or saw, right? So this is the thing actually happening. And some ASIC is fully customized, which means it already fully manufactured. We cannot change the logic also, and this is high performance, which means here it having only particular logic. Okay, according to that logic, it can work, right? So it will having more performance because it is having only particular logic only. According to that logic, it can work. and high cost, right? And development time is high. Why development time is high? Because it will completely the logic will write in RTL, and after that physical implementation is done in PD people, and after that they'll fab people is going to be manufactured it. So to complete all this process, it will take some time. Okay, and fixed functionality, right? We cannot change the functionality also, but in particularly in FPGA, okay, my development time is less. Why? Because we are not going to manufacture anything, right? So that's why it will take not that much of time as compared to ASIC. And it is FPGA is like a flexible. Flexible means we can use however we want. Okay, and it is faster time to market. Why faster time to market? Because it will take less time for manufacturing, because we cannot manufacture any logic in it, right? So unit cost is high, and moderate performance, and performance is also not up to the mark, okay, as compared to ASIC. Why? Because we are changing the logic, right, however we want. That's why somewhat process is somewhat is okay. And ASIC design flow. ASIC design flow. So, what is meant by ASIC design flow? A structured sequence of a steps to transform a concept into a physical chip that is going to be ready for fabrication. So, let us assume we are having, you just want to buy one car. Okay, let us think this is a car. Okay, so let us assume, okay, so this is a car. Okay, for this particular car, we are having some specifications. Okay, so if I want to buy a car, we are having some specifications, right? What is the color of the car and what is the mileage of the car? Okay, so kilometer per hour and everything we are checking, right? These are all known as some specifications to that car. So if you want to same like this example, so if I want to make one same, this is my AND gate. Let us think this is my AND gate having A and B as inputs, and Y is my output. So by seeing the drawing itself, we can say that this is my AND gate, and my AND gate having A and B is the outputs, and Y is the output, and we know the functionality of that AND gate also. Whenever we are giving the inputs, both inputs as high, then only we'll get the output as high. This is the functionality of AND gate, right? So by seeing the picture itself, we can say, but how a tool will understand, right? So I just want to make this logic. So before going to make this logic, we need to give some specifications. What are the specifications of my logic? So this is my logic, right? This is my logic. Okay, so we need to specify the specifications, right? So what is the specifications of this logic? So we are having two inputs. Those two inputs are A and B, and we are having one output as Y, and we need to mention the functionality also. Whenever I'm giving the inputs as 1 and 1, which means high, then only we are getting the output as high. So these are the specifications we need to enter in the specification stage. So after going to specifications, RTL design. So RTL people, what RTL people they'll do? So up to now we are having some specifications. So according to that specification, RTL people will write the logic in Verilog or else VHDL format. So they'll write the code. So module. Okay, I'm not going to explain the complete RTL code. Okay, so they'll name it as module and module name. Okay, after that they're going to add some logic as my A is equal to A and B, right? So they'll write the logic and they'll end the module. Okay, they end module. This is how they are going to be. Okay, so this is the some of the very small logic, right? So this is how they are going to write the logic in RTL by using Verilog or HDL format. After write the code, then need to check the functionality whether it is working properly or not compared to that particular logic. We need to verify the functionality. If my verification is failed, then we need to again change the logic. Okay, so according to that okay, according to the functionality of the particular logic, we need to change the code, right? So if my functionality is performed better, then we are moving to synthesis. Okay, 1 minute, I'll erase all the things. Okay, so after that synthesis, so what this synthesis people will do? So up to now we are having functionality. After functional verification, we are having some verilog code, right? So this verilog code is particularly main input for this synthesis. Okay, so in this synthesis, what they're going to do means, for this verilog format of code, okay, we can get the output as netlist, gate level netlist. Okay, we are going to have one netlist file. Okay, we are having some gate level netlist. How? So what is the meaning of synthesis means? Synthesis will do translate this verilog code into a particular gate level netlist. So same logic is there in between this verilog file and netlist file. So what is the major difference means? See, so up to now we are having some logic, right? AND gate logic. So for this particular Verilog format, we are having logic, right? Y is equal to A and B. That is the logic, right? Y is equal to A and somewhat A and B. So up to now we are having logic as in this Verilog file. So coming to netlist, so which type of AND gate we are using? Okay, according to the nanometer, we need to mention all the things. So which type of AND gate we are using? So how many inputs, which means two input AND gate or else a four input AND gate. So whether it is a 2 input, 4 input or 6 input AND gate, the logic will be same for all the AND gates. So that logic is we mentioned in Verilog, and all the technology related things, which means what is the size and which type of AND gate we are using, what is the technology, and how many inputs that AND gate having, all those information is presented in this netlist file. Okay, so for this netlist file, we are giving some SDC file also. SDC. Okay, so along with this Verilog file, we are giving HDC file also to the synthesis. Okay, SDC is also one of the input file for synthesis team. So in this SDC means synopsis design constraints. Okay, so this file contains the complete timing related things. Okay, we are creating the clocks. Okay, we are creating the clocks and input transitions, output transitions, input loads, output loads, all the information is presented in these SDC files. Okay, so up to now we are having netlist file. Okay, so see here, from here PD people will coming into the picture. Okay, so after synthesis, we are having one netlist file, right? So netlist file is the one of the main input for the PD people, right? So why? Because this netlist file contains the complete logic, right? So after synthesis, we are going to move to floor planning. Okay, what is meant by floor planning means? Floor planning is like a same like a house planning. So I'm having one particular area, I'm having some square feet of area. So in this particular square feet of area, I just want to construct rooms. So these two are my bedrooms, and here I'm having one kitchen, and here I'm having puja mandir, and in between both the bedrooms I just want to construct one, what is that, some attached washroom, and here is my entrance. Okay, one of the entrance, and here also we are having one entrance. So for this particular area, we are planning some house planning. So how we are planning, here I'm having I need to construct two bedrooms, one kitchen and puja mandir, like this. So same in physical design also. Okay, So we are having particular width and height of the silicon chip. So this is my silicon chip. Okay, so we need to mention the height and width of the silicon chip in floor planning stage, and after that input ports, output ports, and we are placing the macros. Okay, so how, according to the design we need to place all these things. Okay, in floor planning stage. Okay, in floor planning stage we need to decide the height and width of the core. Okay, so this is the height and width of the chips, and placing input output ports, all the things is done in floor planning stage. Okay, so after floor planning, okay, we are having one step called as placement. Okay, sorry. So up to now we just place the macros and input output ports. Macros means memory cells. Okay, so it is also a some of the standard cells. Okay, so up to now we are not placing any logic in it, right? So in placement stage my actual logic is going to take place. So after giving the placement options, then my complete logic is going to be placed in this particular area. Okay, so this is the thing happening in placement. So after that we are having one step called clock tree synthesis. So we are just place the logic, right? So up to now in the place, up to the placement stage we are just placing the complete logic, which means we are placing the standard cells, okay, into this silicon chip. But in clock tree synthesis we are giving clock to every sequential cell, right? So in my logic I'm having some count of sequential cells, so we need to give clock to every sequential cell, right? So with respect to the clock only my sequential cell is going to start work, right? So that's why in my logic contains so many sequential cells. Okay, so for that sequential cells we need to apply the clock. So that is the thing happening here. So in clock tree synthesis we are applying the clock to every sequential element. Okay, so after that we are having step called routing. Routing means, so up to now we are just place the logic and we are applying the clocks, but we are not connecting the standard cells, right? We are not connecting the complete logic. So in this particular routing stage we are going to connect all the logic by using some metal wires. Okay, by using some metal wires we are going to connect all the logic. Okay, so this is the thing happening in routing. So after that also we are having some specific physical verifications. So up to now physical implementation is completed. So after that we need to check, right? So before going to tape out means that file is we are giving to the fabrication people for manufacturing. So the main output for PD people is this GDS2 file, graphical design system, or graphical design system. So this file is this is the 2 means version 2, guys. Okay, this is the file we are giving to the fabrication people. So according to the specifications in the GDS2 file, so this GDS2 file is contains the complete information of all these physical implemented things and all. So what we do up to now, that the complete logic is there in that gds2 file. So we are giving that gds2 file to the fabrication people, and they'll start manufacturing according to that specification. Okay, so after that we are having packaging and testing. So this is the final step in ASIC design flow, from specifications to packaging and testing. So this is how it is going to be work. Okay, and industries. After that, technology node. What is mean by technology node? Technology node is a manufacturing process specification that defines the smallest feature size, which means transistor's gate length. See, so I'm having one transistor. Okay, so this is my source and this is my drain. Okay, let us think. This is my transistor. Okay, so in between that we are having gate, right? So this is the gate terminal. Okay, so here we are having some channel in between my source and drain. Okay, by using this channel is acts as a bridge in between source and drain to pass the to conduct the current in that particular transistor, right? So if I just want to give any VD voltage here, Okay, then it will transfer the voltage from source to drain. So by using this channel, this is known as channel, so by using this channel only it will transfer the voltage and it will conduct some current in that particular transistor. So as compared to 130 nanometers, okay, in 130 nanometers my transistors length is more, gate length is more. Gate length means this channel length, okay, this length from source to drain, this is my channel length. So in 130 nanometers my transistor's gate length is more. If my transistor's gate length is more means obviously my transistor size also more, right? That's why we are placing only few transistors in that particular area, right? So after that we are having 90, 65, 28 nanometer and 7 nanometer. We are here at 7 nanometer technology. So compared to 130 nanometer, in 70 nanometer, okay, in 7 nanometer, my this length is very less as compared to 130 nanometer. If my channel length in this particular transistor is less, then obviously my transistor size also becomes less, correct? If my transistor size is less means we can place more transistors in this particular area, right? So that is the thing here happening. So if you are having smaller nodes means we are having more transistor density, which means we are placing more transistors, and my performance also better, and my power is also less. It will take the less also within the budget, and smaller nodes, right? That's why fabrication cost is somewhat more. Why? Because we are placing more number of transistors, right? That's why fabrication is somewhat difficult, and cost also, obviously cost also increases. So this is the integration, this is the technology node, how it will directly affects the VLSI node, okay. And after that some transistor. So transistor is, acts as a small electronic switch, right, agree? So when we are, see, this is my CMOS transistors, let us assume, okay. This is my PMOS, and then this is my NMOS. Here we are giving the logic at the gate, and this is my VDD, and this is my VSS. So here we are giving to take output. So what happened when we are applying the gate voltage as 0, then only my PMOS is going to be work, and there is a one connection from this VDD to output. Okay, one path is created from VDD to output. Whenever my PMOS transistor is conducting, then we'll get the output as VDD, right? So whenever we are changing the logic, obviously my output will changes, right? So it is acts as the on or off switch. On means, right? So whenever we are applying some logic at the gate, according to that logic my output will changes. So same like in switch also, whenever we are switch on the chip, switch on the switch, it is going to be work, right? So same here also. So whenever we are applying the gate voltage, then only it will start working, and it will give the output. In VLSI will make millions of these switches work together to perform a task. Okay, if you want to perform a task, okay, we just want to build some logic by using these transistors. Okay, so if you want to switch the logic from one place to another place by using these transistors only, we can do. Okay, so this is the how things are happening. Okay, and what is mean by CMOS? So CMOS is a complementary metal oxide semiconductor, right? So we are having two different things, pull up and pull down. Pull down, right? So for pull up we are using PMOS. Okay, for pull up we are using PMOS, and pull down by using NMOS we are going to construct, for by using NMOS we are going to construct pull down transistors, right? So NMOS will turn on whenever we are giving the logic as 1, which means, see, so this is my pull up PMOS and my pull down NMOS. Okay, so this is the gate, right? Here VDD, and here VSS. Okay, here we are checking the output. Okay, so whenever we are applying the logic as 0, okay, so whenever we are applying the logic, we are having some notch here, right? So this notch will access the inversion of the transistor, which means whenever we are applying the 0, then only it will start conducting. At that time this NMOS is in off because we are applying the gate voltage as 0, right? So this is how a PMOS is going to work and NMOS is going to work. And whenever we are giving the logic as 1, then my PMOS is going to be off and NMOS is going to be on. Understand? This is how it will work, and PMOS turns on with logic 0. Okay, when my PMOS is going to be work, whenever we are applying the gate voltage as 0, then only my PMOS is starts conducting, right? And they'll work together. So they'll work together, but at the particular time only one transistor is going to be work. So here we are having two cases. So in the first case only PMOS is going to be work at the time NMOS is in off. But after we are changing the logic to 1, then what happened? My PMOS is going to be in off condition. At the time NMOS is in on condition. So what we are going to observe here, oh, at the same time we can on only one transistor in one particular logic, right? That's why at that time another logic is in off condition. So that's why it will take less power because another transistor is in off. If my transistor is off means it will not consume any power also, right? So that's why, and it is faster for switching and efficient also. So this is the thing CMOS. And after that we are having basic CMOS inverter. So this is my CMOS inverter. Okay, so this is the truth table for inverter. So here we are applying 0. So then what happened? My PMOS is going to be work and one path. Okay, so whenever this transistor is on, then one path is happening from VDD to Y, and we can get the output as VDD directly. VDD means obviously 1, right? So after that we are applying the logic as 1. Then what happened? This PMOS is in completely off condition, this NMOS is in on. So whenever my PMOS is on, then it is acts as the open switch. There is no path from VDD to output. Okay, and at that time we'll get the output as 0. So this is the thing. Whenever we are applying the logic 0, then we can get the output as 1. Whenever we are applying the logic as input voltage as 1, then we can get the output as 0, which means it is in inversion mode, right? So it converts 1 to 0 and 0 to 1. Both NMOS and PMOS connected together. Okay. When my input is 1, then it is going to be give output as 0. When my input is 0, we'll get the output as 1. This is one simple CMOS inverter. Understand? So after that we are having CMOS logic gates also. So this is the NAND gate. How a NAND gate will perform? Okay, whenever my output both the output as 1, then only I'll get the output as 0. Okay, so this is the truth table for NAND gate, right? So we'll check. So here I'm giving the A as 0, A is 0, and A0 and B0 case. First case I'm explaining here. So at that time what happened? So whenever we are giving this logic both A and B as 0, then my PMOS is going to be on. So whenever my both the PMOS is in on, then one path is created from VDD to my Y. Okay, then what happened? We'll get the output as VDD. VDD means 1, right? So after that we'll check for this 1 case. So here I'm giving the 1 and 1. So at this time what happened? So my completely my pull up transistor is in off condition. Why? Because we are giving the input as 1 and 1, right? So whenever we are applying the inputs as 1 and 1, then completely my pull up transistor is in off state. So at this stage there is no connecting path from VDD to Y. So at that time we are getting the output as 0. So this is the NAND gate. If I want to construct AND gate means how we can construct? So we are having a NAND gate. So for 1 minute, I'll erase all the things. Okay, so here we are taking the output, right? So for this particular output, here we are connecting the inverter. Okay, this inverter we are connecting at the output of this NAND. Okay, here we are giving, okay, here, sorry, here VSS and VDD and VSS. Okay, so we are connecting this output at this gate, which means we are connecting the output at this gate. Okay, and then we'll check the output here, then we can get the end gate, right? Why? Because the inversion of end gate means NAND gate means end, right? So that's why we are connecting the inverter to the particular. 1 minute, guys. So sorry for the delay, guys. So this is the complete thing related to particular end gate, right? So understand. So after that we are why CMOS is popular. So why CMOS is popular now only I'll discuss, right? So we cannot switch on the both the transistor particularly at same time. Then what happened? At that time we can save the power, right? So it will take only less power, only use power when switching. It will only take power when it is in switching, right? When we are switching the data, then only it will take the power. And high speed operations also and scalable, can be made very thin, which means nanometer. We are working in the nanometer technology, right? Which means very small things. Okay, and it will take less heat also. Okay, so this is the thing happening here. Okay, and these are the some of the applications. Okay, so where CMOS is used everywhere in every electronic component, guys. Why? Because so every component is built by using some transistors. So here we are using CMOS transistors, and then we are making electronic devices, right? So these are the some of the applications like microprocessors, microcontrollers. Okay, some of the memory devices. So everywhere, okay, is some image sensor, analog circuits, IoT, and embedded. Everywhere, in everywhere we are, if you want to design one electronic device means, definitely it will, that logic completely having some transistors. Okay, that transistor is maybe CMOS or else something. Okay, so this is the thing, and that's it for today. And I'll explain in the next class why PMOS is using in pull up and NMOS is in pull down. Okay, and that is the thing. And thank you for today's class. Thank you. So if anyone having any doubts, please contact our team. Okay, we'll help you. Hope you're great day. Bye.